So welcome everyone for the first day-out seminar of this semester, and it's a great pleasure to introduce today's speaker, Dr. Michael Rollins from the Geosciences Department at the University of Massachusetts at Amherst. So Michael did his undergraduate studies at the University of Delaware in Newark, and he majored in atmospherics, in environmental sciences and mathematics. And he did his doctorate at the University of New Hampshire in Durham, and his doctoral thesis was about hydroclimatology, or the freshwater cycle of the Arctic. And he has contributed several publications on this very current topic on how the climate of the Arctic is changing, and especially the water cycle. And after his PhD, he was a postdoctoral research associate at Jet Propulsion Lab for 2 years. And then he joined the faculty at UMass, as I mentioned to you. And recently, he is the lead author of an important publication trying to forecast or project what the climate of the Northeast US may look like a few decades from now, and this is a topic of great interest, so let us see what he has to tell us. So Michael.
Thank you, Professor Hamid. It's my great pleasure to be here today. I'm very much impressed with some of the great research being done in this school. Took a look at the website, some of the faculty and graduate students' interests, and it's very impressive, quite an impressive lists of interest topics. I hope you'll find this interesting as well. Potentially a lot of interactions, potential collaborations with some of this work. I know many of you are interested in climate variability and climate change and its applications. I want to first acknowledge my co-authors on this publication in Journal of Geophysical Research, Raymond Bradley, Henry Diaz. I also want to acknowledge Bill Gutowski at Iowa State and Linda Burns at NCAR, who are the NARCAP principal investigators, and also the NOAA Regionally Integrated Science Assessment Program, who provided support for some of this research being done at the University of Massachusetts. The outline of my talk today, I'll start off with some recent research focused on the Northeast U.S. climate. Start off with some basics of global climate change, and then take a closer look at some climate changes that have been going on and projected for the Northeast U.S. Then take a look at mid-century projections of temperature and precipitation, seasonal, and an assessment of those model projections from these NARCAP models, the North American Regional Climate Change Assessment Program. Then take a quick look at some impacts, some estimates of changes in snow depth for a number of models, and also look at some potential changes in things like growing season length, or the inverse of that, the length of the frozen period. And then I'll finish up with just a few related changes in northern high latitude climate, as that's been an area of interest of mine for the past decade or so. Some interesting research I've done looking at the water cycle there. So if we look at climate change, if we look at the basics of climate change, as most of us know, we have global greenhouse gas emissions increasing. And when we look at this figure here, these figures, let me just use here. There are two projections here. These are these SRES emission scenarios that many of you are familiar with, these projections of how greenhouse gas emissions may change moving forward. And the two of primary interests here are this A2 and this A1B. And if we look at the A2 scenario, it's one of the more aggressive. It shows this really quite alarming rise in these greenhouse gas emissions moving forward. And the A1B begins to tail off here around mid-century. So up to mid-century, these two projections are fairly similar. And we see that there's these projections of global surface warming based on the different scenarios. So we could potentially get as much as 2 degrees Celsius, or as much as around almost 4 degrees Celsius increase by the end of the century, global average. So we have these different projections. We're unsure how the greenhouse gas emissions will change, but we use these scenarios to project what will happen in the future and run these through climate models. Projected patterns of changes. If we look at the global pattern, the global cycle, the multi-model mean. So this is from the IPCC Fourth Assessment Report. Many of you have seen this, a very popular figure, very common figure, that shows, we look at using the A1B scenario and these multi-model means for December, January, February, winter, and summer, we can see this pattern of high latitude wetting. And the stippling is an indication of model agreement. So many of the models agree that you'll have this high latitude wetting increase, and also there are these areas of decreased precipitation under the Hadley cells in the subtropics. And if we look at the summer pattern, the projected changes are not quite as large. I'm not sure of the global average pattern, what we have for the magnitudes, but suffice it to say that we have this projection for high latitude wetting. If we look up here into the northeast US, not surprisingly, we might see that we have an indication of wetting across the northeast up here for the winter. For summer, really that change is probably not statistically significant, and it's very small. We're not sure what will happen there. So that's the global pattern from GCM's Fourth Assessment Report. If we look at North America, 15-model average from the A2 emission scenario. So the A2 emission scenario forced into these GCMs. Winter, again, 15, 20% maybe here in winter. Again, in summer, this pattern, the projections are close to zero. We're just not sure what will happen in the summer. So the global pattern, the GCMs are suggesting that wetting in winter across North America and the northeast US, summer not so sure, and again, in the transition season, spring and fall, not a really strong signal there. Looking at things like intense precipitation, so not only what we expect changes in the seasonal totals or seasonal averages, but very heavy precipitation. So if we look at the historical record, so this is from Pasha Groisman et al. Paper, it shows about a 67% increase in very heavy precipitation amounts, 1958 to 2007. And there's projections from this paper by Bill Gutowski et al. That shows that the lightest precipitation events may decrease and the heavy precipitation amounts increase. So it's a change in the distribution. Wetter for the heavier events, potentially less of these very low precipitation events. So these are projections, and these projections also are for the North America as well.
What qualifies as very heavy?
I don't know for this study. I'm guessing maybe a half an inch, potentially 1 inch. Half an inch is fairly common, but a 1 inch amount is not uncommon to be used in these extreme event assessments. We also expect and see from the historical archive changes in the timing of runoff. So what this map shows is March runoff, and these are observations at a number of gauge locations, where there's river gauging information, where they're getting stream flow estimates. What we're seeing here is March runoff has increased at the expense of May runoff. So what you're seeing is the historical record shows there's a shift in the timing through these regions. And we can see, I don't have a good assessment of, I haven't looked close enough at this to see the spatial pattern where, but we can see in the northeast here, generally increases in the March runoff, decreases in the May runoff, and interestingly, we see in the, both March and May increases out here in the Midwest. So over the northeast, we're seeing this shift in the timing of the snowmelt runoff pulse. So a few years back, a study was initiated which resulted in a publication titled The Northeast Climate Impacts Assessment, NECIA. This is a very comprehensive document. If you haven't seen this or haven't gotten a copy of this yet, I urge you to do so. It's available by PDF. It's about 100 or so pages. but it steps through really nicely all the basic science of impacts to temperature, precipitation, stream flow, heat indexes. One paper of one particular author, Catherine Heo, published a number of studies. I'll touch on a few of those here briefly. But this is really the state of the art. It's published a few years back. Really the state of the art in assessments of the climate changes we can expect to see and that are occurring across the Northeast U.S. So major findings, just really quickly, major findings of the Northeast Climate Impacts Assessment. They projected from this study that over the next few decades, changes in temperature and precipitation are similar for the low and the high emission scenarios. So they used the high emission scenario, the A2, in the GCM runs, and they also looked at a more subtle increase, I believe that was the B1 scenario or the A1B, 2.5 to 4 degrees Fahrenheit in winter, 1 to 3 in summer. By 2100, winters could warm by up to 8 to 12 degrees Fahrenheit and summers 6 to 14 by the end of the century. As winter temperatures rise, more precipitation will fall as rain and less as snow. That's intuitively obvious. And by the end of the century, the length of winter snow season could be cut in half. The frequency of late summer and fall droughts is projected to increase significantly. And this was based on a study using GCM data for the Northeast U.S. And seasons will change significantly, with spring arriving potentially 3 weeks earlier by the end of the century. Okay? So these are the major findings. There's a number of others. I've kind of highlighted the increases or the changes in temperature and precipitation for the NECIA. Okay? So this is one figure from a paper by Catherine Heo in 2006. It's a little bit busy. Let me just break it down really simply here for you. What we're looking at here is temperature and precipitation, the annual winter and summer seasons, 3 emission scenarios, 2 time periods. Okay? So let's just focus on a few of these changes, just a couple real quickly here. Winter from the A2 scenario over, let's term that mid-century. So mid-century, 2035 to 2064. Projections are about a little under 2 degrees Celsius for winter. Summer, a little bit greater than 2 degrees Celsius. And for precipitation, winter, looking at about 8% there for the A2 scenario over the mid-century period. Okay, so just a couple of numbers there to keep in mind. About 8% for precipitation increase in winter. Summer, you can see these bars indicate the range across the models. A lot of uncertainty, very little change in summer. Winter, about 8%. And temperature increases right around just a little bit below, a little bit above 2 degrees Celsius. Okay? This study was using 9 atmospheric ocean GCMs forced with these number of these scenarios. So regional climate models. When we talk about using regional climate models, what we're talking about here is a process where we have, well, we can start with, we know we have a number of observations. So we have a number of observations here at station locations. We can use those observations to force GCMs. So you're seeing here over the Northeast, we're looking at what, maybe let's say a half dozen grid cells from the GCM runs, and then we can use these GCMs to force regional climate models, dynamical models that are forced with the boundary conditions from the GCMs, or those GCM data can be used to do statistical downscaling. So there are 2 different ways we think about downscaling. A dynamical, using a model, a physical model, or a statistical model to downscale those GCMs. Okay? So the NARCAP, the North American Regional Climate Change Assessment Program. This was a project, it's funded by a number of different agencies, NOAA, NSF, NASA, 4 global climate models and 6 regional climate models. So we have a suite of 6 regional climate models, 4 GCMs. And the idea was to develop these high-resolution regional climate assessments for use in impact assessments. Okay? So a number of different institutes are participating. You have institutes, centers that are running these, developing these regional climate models, and they took GCM data and forced their models. Now, if you take 6 regional climate models for GCMs, that's a potential 24 different iterations, pairs you want to call them. I'll refer to those as GCM-RCM pairs. It was decided that would be a little bit too arduous for the modeling groups, so they went with 12 pairings. So each of the 6 RCMs has been forced by 2 GCMs. Okay? They have a matrix where they show which RCM is forced by which GCM. Okay? The NARCAP domain, North America. This is a map showing the domain and showing this is elevation from one particular RCM. And if you're unfamiliar with how this actually works, what is done is traditionally is if this is the domain, we can set up a box, a rectangular box outside of that domain, and the GCM boundary conditions. So you have GCM information at the boundaries, and then that basically creates weather in the regional climate models. What you want to do is if this was the domain, let's say the domain for your, if you want to set a regional climate model over the center of the US, right there, a box, you want your GCM domain to be bigger, and then they toss out the information right in the boundary there between them. You want to have some area where the model will actually spin up its own weather. You have to give it a chance to spin up the weather, and then you can look at the results inside that box. So these boundary conditions on the borders, obviously the western border, when you have the westerlies, the western border is probably more important to get that right out of this area than what's going on in the east because of the westerlies. Okay? So that's the setup of the GCMs. You have AOGCMs. It was chosen, decided to use just the A2 scenario in these forces. You can imagine if you try to do too many model runs, too many mission scenarios, it's too much computationally intensive, it can't be done. So they decided to stick with the A2 scenario. It was argued for 2 reasons. One, the A1B and the A2 don't diverge until mid-century, and we're currently on a trajectory of higher emissions anyway. So the A2 scenario is not, it's not unreasonable to choose that for these mid-century projections for these runs. Okay, so just another schematic. You have the A2 emission scenario. You have a number of GCMs. Here, this GFDL, the Canadian model, Hadley model. Sorry, I can't recall what that acronym stands for. There's also these time slice experiments. We'll let that go for the side now. We won't talk about that. But what these boundary conditions do is each of those, so 2 of these, so let's say the GFDL model would force the MM5 and the RegCM as an example, and they were done over 2 30-year periods, 1971 to 2000, 2041 to 27. These aren't transient runs running through the whole time period from 1971 to 27. It's 2 30-year simulation runs for this project. Also the time slice experiments, which I won't go into, but those data are available. I also want to mention that these RCMs initially in the phase 1 of the NARCAP were forced with NCEP-NCAR reanalysis data. Okay? So the NCEP-NCAR reanalysis data is the best forcings. That's viewed as the best forcings, and that was run through the RCMs, data made available, and publications and studies done to look at how well the models reproduce current climate using the best possible forcings. That's your target. Now we expect that when we force these RCMs with the GCM data that the results may not be quite as good as forcing them with the reanalysis data, which is our best depictions of the current climate for the forcings. Okay? So what this shows is, this shows that over the Northeast US, for this particular model, this is the Canadian model, there's about 250-kilometer grids. This is the native grid for that one particular model. Each RCM has its own native grid. I've done some work where I've snapped all these to one particular grid resolution to facilitate analysis. In the station network, these dots are stations in our station network. The station network over the Northeast is pretty good. If you look at the Arctic, obviously it's much more sparse, so we feel like we can get a really good field of current climate based on the observations here with a station network like this. So the NARCAP user community, 3 main types of NARCAP users. There's folks who want to perform further downscaling. There's folks who want to use these results for performing impact studies. And then the last group is the group I fell into here, is want to use the NARCAP output for looking at regional climate I looked at seasonal climate over the Northeast US, okay? So Linda Mearns just published a paper just recently, just came out, looking at the phase 2 results, looking at the GCM data, the RCMs as the RCM data as forced by the GCMs to look at 2 questions. How do RCM simulated climate changes differ from those of the parent GCM? Really important question to ask. And how important are the relative contributions of RCMs and GCMs to uncertainty for different seasons? What they found was the RCMs tend to produce stronger climate changes for precipitation. Okay? So they enhance wetter and wet areas, drier and dry areas. GCM explained more the variance for winter temperature and the RCMs for summer temperature. Okay? So they concluded it's important to have an equal balance between GCMs and RCMs. So in future studies, you may want to have 5 RCMs and 5 GCMs, is what their salient findings were. So on to the results of my study, and what we're looking at, I'm not going to go into all these individually, but what we're looking at is we have 4 seasons, 9 model pairs. At the time of this work, I was not able, we did not have the 3 remaining pairs that are available. So I had 9 GCM, RCM pairs available. You have a multi-model mean, and then you have, for let's say, the multi-model mean, temperature projection for the Northeast. This is average over the Northeast, about minus 6.5 degrees C. And in the future, we're looking at about, that's about minus 3.5 or so. Okay, so you have 9 models. You can generate a multi-model mean, 2 time periods, 4 seasons. Okay, now I'll try to distill this down. First thing I did in this study was I took a look at how well these models represent the current climate. So I have 200 grid cells. We have a number of comparisons. We're going to look at what's the correlation at the grid cell level, and also what's the spatial variation as measured by something like the standard deviation. So these Taylor plots, essentially, if the RCMs reproduce the current climate precisely, correlation of 1, exactly the same standard deviation, the number would fall right there, 3.2 for winter. Okay, 3.2 standard deviation, and the radial is the correlation. Okay? So what we see here is the correlations are generally around 0.9 for winter, so the good correlation, and the standard deviation is a bit lower in the models and the observations. So generally what we say is, and here for spring, you can see that most of the models, the standard deviation is just about right. Correlation is about 0.95. So for temperature, good. The models reproduce the current climate fairly well as far as the spatial pattern and the correlation. Okay, the variability and the correlations. So in this study, I did 2 different methods to evaluate the changes. One was called the Reliability Ensemble Averaging Method. Another was a method published by Claudia Tabali recently to look at different model signals. So one thing we want to ask is, how does the multi-model mean change compare with natural variability? If the model projection for mid-century is, let's say, 2 degrees Celsius warming, but natural variability is 3 degrees, well then that signal is in the noise. That signal is not emerging among the noise of weather variability. That's one of the things we're looking at in climate these days, is how are these signals as change related to the natural variability? Do these changes exceed natural variability? Then also we want to look at model agreement. Do all the models agree in warming, or let's say wetting? Do some models say wetter and some say drier? So we want to get a handle on, do the models agree in their direction of change and its significance? Okay. So shown graphically, there's three different scenarios, if you will. We can look at most models show an insignificant change. In this case, we may shade the grid based on the multi-model mean, or we will. We have a case where most models show significant changes. So here this is just a significance level, let's say. 5 different models. Each model shows a significant change, but some of them are saying increases, some say decreases. These models don't have information that are helpful to us. In this case, we don't even shade the grid in a map. And then we have where most models show significant changes and they agree on signs. And that's a case where we would stipple the grid. This is what Claudia Tabali, very intuitive, very simple way of depicting multi-model mean changes. Okay? So air temperature. 4 seasons, winter, spring, summer, and autumn. And what do we see? greater increases in the winter in the northern part of the Northeast versus the southern part, okay? So is this the ice albedo feedback in play, perhaps, in the models? We see that you're losing snow across the north here. I don't know locally, I didn't get an exact number. Some of these approach 4 degrees Celsius, at least 3.5 degrees Celsius by mid-century. So this is changes from the 1971 to 2000 period, 2041 to 2070. All the grids are significant. So all these changes we have for all seasons. The models agree and sign, and they all show significant changes, statistically significant. Okay? Summer, the pattern, interestingly, is reversed. We've got changes around, approaching 3 degrees Celsius down here in southwest Pennsylvania, and only around a little over 2 degrees in Maine. That's interesting. Hypothesis there is you're having this greater warming here getting out toward the southern areas that, I want to say Midwest, and some of that's affecting here in the southwest portion of the domain. The biggest changes in winter, alarming changes upwards of 3.5 degrees Celsius, and all the grids show significant change. And interestingly, spring, a much smaller change versus winter. Okay, so that's the air temperature patterns, projected changes. Now we can look at also the distribution. So the distribution for winter, spring, summer, and autumn, what we're looking at here is for each season, O is for the observations. So this is the distribution, a box plot, of the distribution of those 200 grids, the seasonal temperature change over winter for the observations. So you can see that each of these lines, this is actually the 5th percentile, 25th, mean, median, 75th, and 95th percentiles. So we can see that there's a bias, right? The models, present period, so this is observations, present, and future from the models. There's a bias. Well, it's a little over, maybe it's about 2 degrees Celsius. The models are showing a cooler contemporary climate, slightly cooler. And then the future projections. So what we can take from this is a couple of things. One, the distribution is similar from the NARCAT models present and the observations. And the distribution is relatively, maybe a slightly smaller there, but the distributions are similar and they don't change. The distribution, you have a shift, a warming, but the distribution doesn't widen or narrow, okay? Fairly normal distributions. And also the increase, so the change here slightly exceeds the bias. And that's information we want to know. We want to know, does this projected change, is it larger than the bias, smaller than the bias? It's a metric that we have to give us confidence in our changes. Okay? So you can see here that about equal, and I have a summary of some of these change numbers, about equal changes you can see just by eyeball. Each season we have a slightly cooler model projection of current climate versus the observations. This is for temperature. Okay? Precipitation, we have the same models, 9 models. We can generate a multi-model mean, 4 seasons. Okay? Northeast U.S. So these are averages over the Northeast U.S. We need all these numbers for each of these models. Look at the Taylor plots. So if you recall, temperature, good correlations, close to standard deviations. Here are the correlations. You can see the correlations, 0.4 to 0.5. These rays here are the levels at which we have a statistically significant correlation. That would seem pretty low, but that's, in fact, you get a statistically significant correlation. This is 90th and 95th percentile. Okay, so winter precipitations, any season, the correlations aren't as good for precipitation. Okay, particularly in summer, right? We have a convective regime. These models just don't do as well with precipitation as they do with air temperature, not surprisingly. So the standard deviations and the correlations just aren't as good for precipitation as they are for temperature, and that's not surprising. So we can look at the distribution as well. This here on the left, this is our temperature box plots here for comparison. So what can we see for the precipitation? Well, we can see a couple things. There's a positive bias in each season except for autumn, which is interesting. Now, I'm not showing the paper has these maps where I showed biases, the spatial pattern. There are some indications that the bias may have a spatial pattern, that the bias, you can call it error if you like, in the model depictions of current climate may be have a spatial pattern where your biases are wetter toward the coast or larger toward the coast versus inland. But I'm not showing those here. But what we can see is the bias is positive each season. So we have, let's say, a distribution average of about 230 millimeters here in the observations, and the models show about 265. Okay, so we're wetter each season. The models, RCMs as forced by GCMs, are wetter than the observations in most seasons, except for autumn. Now, what we're wondering here is this should be a really active area. This requires further investigation. Are these RCMs as forced by GCMs or as forced by RCMs? Are they able to capture extratropical cyclones moving up the coast to give us our precipitation in the autumn, or tropical systems? So how well do these models capture the increasingly synoptic as we move into autumn? Right? We're getting away from convective to more synoptic precipitation patterns. How well are they capturing those events? Because you're having positive biases each season, except for autumn. Are we missing something there that's going on in the model dynamics? The change magnitude does not exceed the bias, so we have a bias here, but the change magnitudes are not as great as the biases. And the simulated distributions are narrower than the observed in winter and spring. So here you can see, here's this distribution across all the grids, and the models don't quite have as wide a spread. Right? Not as dry in the dry areas, not as wet in the wet areas. So for precipitation patterns, the change pattern across the northeast US. Okay, what we're seeing here is winter. So if you recall, for the air temperature, the changes at each grid were statistically significant at all grids. For precipitation, that's not the case, but it is for winter. So what we're seeing here is all the models are showing an increase in winter precipitation, statistically significant. So we stipple the grids, and we're looking at about between 10, as much as 15% increase in winter precipitation. Now recall the study from Catherine Hayo, they were looking at changes across the Northeast, about 8%. Here we're showing a little bit wetter, and the paper that Linda Mearns just recently published said the RCMs show wetter in the wet areas, drier in the dry areas. So this is consistent with that. The RCMs, when forced by the GCMs, are showing a bit wetter than the GCMs themselves. And these are these are the A2 scenarios, which was used in the Mearns paper using the NARCAP data, and a Hayo paper looking at 9A of GCMs. Okay? There's also indications that perhaps we'll see an increase in spring precipitation. Now those magnitudes are lower than the winter, but the models are tending to agree. Okay? Summer, it's a different case. Now across the southwest portion of the domain here in Pennsylvania, there is an agreement. Okay? The models are showing statistically significant changes in the same direction, but over much of the region, we just don't have that robust information. In areas here in white, we have models that are showing significant, so the question is, you use a number, you have to pick a number. So you say like 7 of the 9 models show a significant change, then half. You can do this, how you design that is, there's some subjectivity. But for much of the Northeast, the models don't agree. We're not sure if we're going to see increases in summer or decreases in precipitation. In autumn, we're looking at, we have a change signal. We have generally wetter, so wetter here, 2 to 6%, but those signals are not statistically significant. So we're just not so certain. We think it'll get wetter, but we have to wait until the signal emerges from the noise, essentially, for the autumn, okay? So a couple of plots. What this shows is this is our regional averages. Okay, so this is those, if we look at those maps, we can infer what the regional average is. So the multi-model, strict multi-model average for air temperature for winter, spring, summer, and autumn. This filled circle is a multi-model average that is weighted based on how well each model depicts current climate. So if you have a model that's, it does not do well, has a huge bias relative to the current climate, well then you give that model less weight in the multi-model average. Okay? So in winter, we see the multi-model average using the REA method is slightly cooler, but there are similar numbers, and most importantly, these numbers are all greater than interannual variability, natural variability. Okay? That signal, around 2.5 degrees Celsius, plus or minus, each season, is above the level of natural variability. But for precipitation, it is not. Those changes here, that's not significant for summer precipitation. Decrease of 3 or 4%. It's not significant, and it's within the level of natural variability. So you can see here that we have these different levels of confidence for the temperature projections versus the precipitation projections. But it looks like it might be getting wetter in winter. Okay. So now let me shift to a few graphics that show some analysis I did looking at snowfall and some projections for how the growing season or the frozen season may change. Okay. So what we're looking at here is, this is the Northeast again. So this is Maine, hard to see the outline of Vermont. So for these grids that I shaded, we are here. We may be in that grid or we may not, close, but what we're looking at here is we have two different temperature annual cycle here. What we're looking at is for this location in eastern New Hampshire, for this grid here marked 1, and this plot is for 2 out here in western Vermont. And we can see, if we look, and these are decadal averages, okay? These aren't the 30-year, and this is some earlier work I did looking at just the 1980s and the 2060s. So you see these two annual temperature plots. We have the current in black and the future in red. You can see we have this shift upward in the signal, in the annual temperature curve, right? So we can calculate this delta for when the line, and here for this work I used minus 2.2 Celsius, based on some work that a colleague is doing up in the University of Wisconsin, using minus 2.2 as a measure of when vegetation growth begins or shuts down. You could easily just use 0 Celsius. You can think of this as 0 Celsius if you like. So we have this shift, we can calculate this change for when we cross this 0C or minus 2.2 isotherm. If we have this other curve here for Vermont, these annual time series, we have a delta here. If we look at that change, that difference in the length of either the growing season, so this is the change in the frost-free period, so this is the change in the length of you could call this the growing season. We can see in some areas, this change could be upwards of 2 months. In other areas, it's just a couple of weeks. And this seems to be related to the shape of the temperature cycle, right? When we're coming out of winter here, there's a few weeks where we're not changing the temperature very much. We have snow on the ground. A lot of that energy is going into melting snow, changing phase, and not into warming surface. So the question becomes, potentially, are we going to see these nonlinear changes in things like growing season length, the number of heat index, or not heat index, but the heat index, the growing season length, accumulated degree days of heating, degree days of cooling, nonlinear change potentially as we warm. Okay? If we look at this over the whole Northeast, or whole North America, you can see quite well this pattern right along the southern boundary of where we have a cold season. Also did some work looking at the potential changes in the snow season in measures such as winter precipitation, number of cold days, and snowfall. So you could use these monthly, or these are daily, not daily. And I should mention the NARCAP data are 3 hourly. So we have outputs from the NARCAP every 3 hours for those 2 30-year periods. So looked at a number of different, so I pulled out the number of grids for a number of these locations. These are ski resorts in the Northeast. And basically what we see is winter precipitation projected to decrease, or increase, I should say, winter precipitation increase for each of the models, okay? So each of these models, but there's quite a large range across the models. There's a much smaller range in the depictions of the current precipitation than the future projections, but wetter in winter, right? Well, wetter and potentially more winter, December, January, February precipitation. Now this is not snow, sorry. This is just total winter precipitation. Winter precipitation might go up. What does that mean for the ski resorts? Okay. Annual snowfall. Okay, so if we take and accumulate all the snowfall, so this is just using temperature and precipitation data. Snowfall projected to go down, okay? We're losing snow on the edges in November and let's say March, we used to have. Again, much larger range in the future projections of annual snowfall than the current. And this is just using, again, temperature and precipitation data. Decrease of about 20 to 30%. And this is different. And I haven't had a chance to look at this pattern and see if there's if the pattern makes much sense as far as the north to south in these. Some work I did with some undergraduate students in a class project a few years back. Number of days below -2 Celsius. Okay, snow making ability. It may not snow, but they can still make snow. Well, this is quite alarming. If we look at some location, Camelback, a number of years ago when I used to live in Delaware, went skiing here at Camelback. Right now, they've got about 45 days a year where they can make snow. May only be down to about 5 in the future. Okay? So we could use these data to look at impacts to ski resorts, snow season. I've taken a look at some snow depth data from the NARCAP models. At the time that I looked at this, there were only 3 models that had snow depth data up on the archive. I anticipate that assume that there's many more now. You may have at least a half dozen, maybe 8. I'm assuming all the models make that available, the snow depth variable. What we're looking at here is I took 3 of the RCMs, GCM-RCM pairs, snow depth fields, and averaged them for December, January, February. What this shows down here in the lower right is this is the actual National Weather Service data for Syracuse. Okay? Syracuse has seen a statistically significant increase in snowfall, seasonal snowfall, over the past half century or so. Okay? But if we look at these NARCAP models, particularly in the lee of Lake Ontario, not surprisingly, we see declines in the snow variable in the models, decreasing snow depths. Okay? And but interestingly, there is some hope, okay, for upstate Maine. The models itself, now not using temperature specifically, the model snow depth field itself shows that in January, we may have deeper snows in January. Okay, so we're looking at about 20, 30% deeper snowpacks potentially in January. Okay, so contract your season, maybe no longer season-long lift passes. You may want to just get a lift pass for the month of January. Lastly, I want to touch just briefly, just a couple of slides, looking at some work I've done, looking at the Arctic freshwater system, Arctic climate, projected changes, some attribution studies for river discharge. Back in 2010, I published a synthesis paper with a number of colleagues. This was a capstone study from a National Science Foundation freshwater integration study, multi-million-dollar project funding a number of investigators and a number of institutions to look at the freshwater cycle. And the capstone study we published looked at the Arctic system. Is the freshwater cycle intensifying? Models projected as we warm, we hold more moisture, we can precipitate more. The dynamics are such in the Arctic that we can get more precipitation, more evapotranspiration, more river runoff, more net precipitation. So we looked at the data. This is mostly from observed data, gridded fields from observed data, but we did look at a number of models for some fields where we needed to. Okay? So we looked at Pan-Arctic precipitation. So these are the number of different data sets. Some of you may be familiar with the ARA Interim. This is Global Precipitation Climatology Project. This is the Climate Research Unit, CRU. This is the GCMs. So if we look and just do a Pan-Arctic, so this is the signal averaged over the Pan-Arctic drainage basin. So this is the area draining to the Arctic Ocean. We see a statistically significant increase in precipitation going back to 1950. Okay? Some of them show greater changes than others, and the GCMs also show that. So if we look at GCM data, and studies have been done over the past few years, they project the wetting in the Arctic. Okay? And we think we've seen this. The signal is beginning to emerge. You see noise, there's a lot of interannual variability, but the signal is significant. Okay? The signal is emerging from the noise. If we'd have done this back 20 years or so ago, maybe not. If we look at evapotranspiration, now we needed to use numeric models for this, but they show a similar pattern. Now some of them, the magnitude of ET from the Vic model is rather low, so the magnitudes may be a little bit questionable, but also a significant increase. Notice that variability with the GCMs is lower. The GCMs have a higher statistical significance because the interannual variability is lower. For the same level of trend slope, lower variability, higher significance. And river discharge, regional and Pan-Arctic river discharge. River discharge is going up. Okay? We use different measures. We have the GCMs, not quite as wet as the observations, but this is mostly based on observed data, gauge observations, and river discharge has probably the lowest uncertainty of all the fields. If you want to look at a region across the Arctic, precipitation, you have a very sparse network, you have gauge undercatch, windy, turbulence over the orifice. Precipitation, you have uncertainties, evapotranspiration, even less data points for ET. River discharge, because it integrates across an area, and those uncertainties are much lower. For the Russian rivers, for annual total, maybe 3 to 5% uncertainty error. Maybe a higher error in winter when you have a lot of ice, but the uncertainty is much lower in the river discharge signal than precipitation or ET. And then things like groundwater, fluxes, and snow, hard to get snow from remote sensing, even more sparse. Okay? So a few years back, Bruce Peterson at the Marine Biological Lab published a paper in Science documenting a significant increase in river discharge from large Arctic rivers. So what they did was they took the river discharge data from the downstream sites of these large Eurasian rivers, the Ob, Yenisei, and Lengya, the three biggest, took the river discharge annual total each year, totaled it, and then drew the time series plot. There is more water flowing through these large watersheds of Eurasia to the Arctic Ocean. And you can imagine this has profound implications for things like the meridional overturning circulation in the North Atlantic, get too wet, too much fresh water, for the food web in the coastal oceans here, for anything that's water moving through anything living in the rivers. So this increase, and this is the North American rivers, are also beginning to show this much shorter time series for the North American rivers. But going back, the Russians have been gauging these rivers and measuring discharge back to the 1930s. Okay? So if we want to look at just these large watersheds, just the signal from these large watersheds, and this is capturing much of the flow from that region. And if over the Pan-Arctic, most of the water, you have more water coming from Eurasia than coming from North America for a Pan-Arctic total. Okay? So a very significant increase, about 7%. 2007, the total from 2007 was 25% above the long-term mean. Just a massive flux of fresh water. It looks like it's related to increasing snow. Okay? So I published a number of papers over the years. So as soon as this study came out, the attribution studies began in earnest. Anybody want to take a guess of what's the first thing you want to look at? River discharge is going up.
Suppose Peterson related it to NAO.
No, I wouldn't look at NAO first. But you want to attribute, where's all that water coming from?
I think so.
I want to look at precipitation. What's annual precipitation look like? Let's draw the annual precipitation. They drew the annual precipitation curve, and it was flat. And folks started saying, where is this water coming from? Doesn't look like it's coming from precipitation. Can it come from dewatering permafrost? We're thawing permafrost, locked up frozen water for tens of thousands of years, and now we're dewatering it. And that looks like you couldn't get it from dewatering permafrost, or fires, or dams being put in. Okay? So I began to look at seasonal precipitation. Let's look at winter and summer separately, because we know that the efficiency when we have snow, we get a lot of runoff from snow, less from summer rain. We can just infiltrate that, store it, ET it back out. So I started looking at snowfall and rainfall separately across the region. And found that there's positive trends in cold season precipitation across north central Eurasia. But since I looked at an integrated signal over the region, it wasn't a very strong signal. Then I began to look at spatial patterns separately in a publication in JGR 2009, and so basically saw that solid precipitation appears to be increasing. At a period of time where solid precipitation is going up, summer precipitation going down. So if you have winter going up, summer going down, you have no change in the annual total, but you get more runoff. Tara Choi published a paper where she used a model, looked at snow melt in the model, and basically found that cold season precipitation propagated into increases in maximum snow water equivalent, which lead to increases in runoff. And Zhangong Zhang at University of Alaska Fairbanks published a paper looking at increased net atmospheric transport. So it looks like basically you're just moving more water from the mid-latitudes up into the Arctic. And it appears that there's more water coming in the winter, less in the summer, and that can explain much of the discharge increase. Another paper came out a few years back, or last year, where they said most of this water could be attributed to increases in winter snowfall. They mentioned the hypothesis of Rollins et al. Kind of nice to hear, but that was my hypothesis originally. That looks to be what's taking place. Okay. So to sum up, the models are consistent. The NARCAP models are projecting an increase in winter precipitation. Uncertainty in precipitation is greater than other seasons, especially summer. We just don't know. Projected air temperature increases to a large spatial gradient, up to 3.5 degrees Celsius in winter in Maine, less so in the more southern regions, but a robust signal of temperature increases slightly greater than what previously has been projected from the AOGCMs. Derived seasonal snowfall at New England ski resorts projected to decline by about 10 to 30% by mid-century. Wetter winter precipitation, but lower total snowfall. And the spatial pattern and changes in growing season and frost season length require further investigation to get a handle on it. Are there going to be non-linear changes in growing season length and frozen period length for a equal change in seasonal temperature or precipitation? Thank you.
Questions for Michael Rock? Yes, Christopher.
How much of the difference between the regional models, where they give you different signs and stuff, comes from differences in the global models, and how much of it actually comes from differences in the regional models?
That would require some further investigation. I'm unaware of. I don't believe that. So Linda Martin's paper, I haven't looked at it in enough detail. I don't think that information is in that recent paper, and I'm unaware of anybody who's specifically tackled that. If you're speaking about a certain region, if you're saying like the Northeast U.S., I haven't looked at that. Honestly, very interesting question.
Very difficult to figure out because each combination of GCM and regional model will give you a different answer.
Yeah, but I think it's kind of part of the question or part of the answer to the question of what does using the regional models actually give you above what the...
Well, if we recall, the Mearns paper suggested that the regional models, the regional models give you, for precipitation, wetter in the areas that are projected to get wet, drier in the areas that are projected to get drier. So the signal from the RCMs is wetter than the GCMs in the wet areas, or in the areas that are projected to get wetter. More dry in the RCMs versus the GCMs in the areas projected to get drier. But that's North America. That's not specific to the Northeast.
Yes, Brian.
I guess just to follow up, you mentioned that the best setup is having a combination of regional and global models, and that's true in terms of applying in the Northeast area. And I'm curious, based on that question, why is that the case? Why do we need a combination of global and regional? What are we getting from both of those together to give us the best prediction?
Yeah, that's some of that information is in the Mearns paper. Again, that's for North America.
Okay.
And again, I think they were looking at the variance, right? I pulled some of this stuff out yesterday, and I wasn't able to get enough into the text, but I think the thinking is because of the different projections of variance from RCMs and GCMs, the thinking was that you need an equal combination. You don't want to have 10 RCMs and each one forced by just 1 or 2 GCMs, because each one brings a different
Yeah, I can understand the diversity of models and wanting to downscale with diversity, but also, maybe I misunderstood. If you're using the output from the global model too as part of the statistics.
I did not.
Oh, well, I know you didn't, but is that what was advocated, is to use, coarse resolution GCM plus NARCAP to get the final answer? Or is it just downscaled NARCAP?
No, what Linda Mearns, with that paper, what they advised was that you, in the context of a RCMs forced by GCMs at the boundary, in the context of that, you want to have a relatively equal number of contributing GCMs and RCMs. You don't want to have too many, but this is all using, in a study that uses the RCMs forced by GCMs. So that's implicit.
So maybe I misunderstood. It's all downscale. We're not using any coarse resolution.
Well,
Yeah.
Mearns, what they did was they looked at the GCM projections of changes just from the GCMs independent of the RCMs. And then they said, well, what do the GCMs project for precipitation changes, and what do the RCMs as forced by those GCMs project? So they made their conclusions based on comparing. And that's, a lot of folks ask, well, what should we use to force these models, and what should we use to evaluate them? Have you looked at the GCM projections over the Northeast US? And I've been asked that. I say, no, I have not looked at that. Now they have looked at that over the North America, and looked at how the GCMs themselves project change, and then the GCMs, the RCMs forced by the GCMs. And I definitely happy to chat with you after this and kind of refine that explanation.
Okay, let's see. Oh, yes.
I think you may have alluded to, but you compare the mid-century prediction and show that model and observation have some difference. And then when you actually make the future projection, since they all depend just on model, else if model all agree, then you can't believe them. So my question is, if you try actually, with the information that model actually have error, how they actually being used in your future projection?
How's the error?
Yeah, because we know the model is not perfect, right? And so when do you actually use that information in your future projections?
So I didn't really project. I'm just using the grid data and grabbing the grid data fields. So the way I used the model quality was in that averaging method, where we weight multi-model average based on how well it depicts. So if you consider an error, how well model 1 depicts current climate versus observations, it has an error. The models that have smaller errors, they get more weight in the multi-model average.
So how do you do that? Just curious. I know. So how you actually incorporate that?
So that's Filippo Giorgi's has a publication where he describes the REA method, and there's an equation where you assign weights.
Yeah, that's what
To get multi-model average.
Yes, if you consider the conservation of water itself, global models will conserve the water.
I hope the RCMs do too.
Well, yes, that's my question actually. We have different RCMs forced by different boundaries from different GCMs. So over that box, of course the box could be slightly different for each RCM. So over that relatively identical box, will the water be conserved during that period of time, or will the difference between each box be small enough?
I don't think there has to be a conservation between the GCM grid box, obviously.
Well, I
So
mean, the total domain, for the RCM.
I wouldn't guess that there's that requirement.
Okay, it appears that the RCM is actually redistributed water over that big domain.
Right, but you remember that you have these boundaries. At the boundaries, you have temperature, you have wind, you have these different conditions at the boundary, and then you let that RCM spin up its own weather. And then what happens once you're inside that domain where you've got weather going on in the RCM? Now you start to say you want to see things balanced.
But the constraint is from the GCM.
Yeah.
There's a constraint.
What the requirements are as far as any type of water balance when you're transferring information from a GCM atmospheric profile.
Right.
And
And
create
again,
a-
water is not destroyed in the water.
No.
It has to be conserved.
Yes.
So, Amazon, what do you want to?
This was about the length of the growing and the frosty season. When you showed the figure, the most red part was towards the southern end, and then it dropped off to nothing.
Yeah, there's no-
What exactly does that mean?
So there's no cold season there. You're never below, never below 0 Celsius.
That one, yeah, that one.
But you can't even talk about a cold season there.
Say what?
You can't even talk about a cold season because it never gets below
But
-2,
don't you think
-2 or
it's-
0.
The seasonal average.
Decade, when you average over a decade, right? You never get below, for those regions there, this current climate, black curve, it's above this line.
Oh,
You don't even have a,
It never gets cold.
okay.
you never get below -2 for a daily average, for daily over a 10-year period, maybe an individual year.
And
One more question. I think you mentioned that the model does well in terms predicting the temperature change. What do you mean by that? What do you mean by that?
They do well in capturing the current climate. We don't know how to do the future.
No, okay. In current climate, in terms the year-to-year change in temperature or just CNO cycle? You always
No, those we're looking at the spatial pattern in 30-year averages.
We should actually diagram it, because you showed the Taylor diagram,
Yes.
the correlation between the models and the current observations are like 0.95. I think your assertion was based on that result.
Yes. But
That's over 30-year.
Over 30 years.
over that region.
Difference.
Yes. That's looking how well they capture like spatial,
Patterns.
not inter-annual.
Yes, Michael.
Is it possible to force the RCMs before removing the mean bias from the GCM?
To force the RCMs,
After removing the bias from the GCM? There's
Um,
mean bias?
I guess the modeling folks could do that. Sure.
Yeah, so before we conclude, so the students who are registered for this seminar, please remember to sign the sheet in the back every week. And so let us thank Michael Rollins for a very, very interesting.
Thank you for your question.